This example comes out of section 9.2, Analyzing Rational Functions. Very similar to our last example, we're asked to graph a rational function that has a quadratic in the numerator and just a binomial linear term in the denominator. And it turns out, it's very similar to the last one, that this thing does factor, and we get x minus 3 times x minus 2 in the numerator over x minus 3. And again, that unique situation where you have x minus 3 on the top and the bottom, meaning that this function basically is going to look like y equals x minus 2, except for the fact that x cannot equal 3. So this is our function that we'll draw here, and x minus 2 looks something like this, and at x equals 3 there's going to be a hole, and so we'll have a graph looking like a straight line except for this one tiny little gap in it. Again, if we want to know where that gap is, if I say y equals x minus 2 and let x equal 3, I find out that that point of discontinuity is happening at 3, 1. There are a number of ways to take a look at this point of discontinuity and talk about the behavior near this non-permissible value. One way is to look at your x and y values and kind of make a table of values and say, well, what happens if I put in, I can't put in 3 into the original function. If I take the original function and say y equals x squared minus 5x plus 6 over x minus 3, if I put in 3, I end up with 0 divided by 0. And you can try 0 divided by 0 on your calculator if you like, but it'll say error, you can't do it. But if I put in 2.9, I can get an answer, and an answer that gives me about 0.9. Even if I go way closer, like 2.999, I can get an answer even closer to 1.999. Even if I go a little bit higher, like 3.001, gives me 1.001 or roughly so. And so you can see that at values very close to 3, this function exists, and not only does it exist very, very, very close to 1. In fact, as close to 1 as you want to make it. If you put in 2.999999999 or 3.0000001, your value is as close to 1 as you can imagine. So I just want to point out one little difference between non-permissible values that we've seen in the past and non-permissible values that we see here in this section, where we're running into these, again, it's a point of discontinuity. Point of discontinuity happens when we have this 0 over 0 situation where we have a factor like x minus 3 on the top, and we have that factor on the bottom. We might have some other factor on the top, as we do in this case, but if we let x equal 3, we get this 0 over 0. It's definitely undefined, but it's also something what they call indeterminate, and that is really more of a calculus term. You'll run into that if you decide to take Math 31 or some calculus down the road. But indeterminate form means you've got this 0 over 0 problem. And in our functions, as we've seen to this point, it shows this point of discontinuity. Often you'll have something like, we've looked at in the past 5 divided by x, or 8 divided by x minus 2, or something like that. And if you put in the non-permissible value in these, you'll get some number divided by 0, 5 over 0, 8 over 0, etc. Now that still on your calculator says error, can't find the answer, but these ones end up more often giving you vertical asymptotes instead. So the difference between a vertical asymptote and a point of discontinuity is kind of the situation. Instead of having 0 over 0, the indeterminate form, you have 5 over 0, 1 over 0, 8 over 0, which is still considered to be undefined. It's just kind of undefined in a different way. And if you were to look at values near the non-permissible value, you'd find that you wouldn't be approaching a number like 1, as we did in the example here above. You'd be going towards infinity or negative infinity, which makes these graphs look quite a bit different, where if I go to an asymptote, I have something that is like this, and like this, approaching pointing almost straight up and straight down as you get close to that asymptote. So just the difference between a point of discontinuity and a vertical asymptote.